So,
okay, our problem was pile splitting. So this is the problem. And it says, so you start with a pile with exactly n chips, and at each stage you can choose a pile and split it into 2 piles. And so those piles, they can have any number as long as they're non-zero. Actually, yeah, I think non-zero. And they add up to n. And so you keep on doing this, and you take each pile and you split it into 2 until every single pile it has 1 chip in it. And so at every stage, you keep track of your score. So your score at every single stage is, your initial score is 0, and so every time you split a pile, you multiply, you multiply like the numbers in the 2 piles, and you add it to your previous score. And so then your final, and so the goal is to get the maximum possible score, okay?
Give an example.
Okay, yeah, we'll give an example. So, yeah, well.
No, we have it in here.
Okay, so.
Yeah.
So here's our first example. We tried 5, and 5 splits into 3 and 2, so you multiply 3 and 2, and 3 splits into 2 and 1, so you multiply 2 times 1 and add it to 3 times 2, and so on.
Yeah, and the score is 6 plus 2 plus 2 is 10, yeah. And so, but then we tried splitting 5 a different way, because there's multiple ways to split it, right? And so we split it.
We split it like where you take 1 off each time.
Yeah.
And it was also 10.
Yeah, and so we were like, oh, this is the same number. That's kind of strange. So we tried different examples, and like with n begins with 6, n begins with 7, etc. And we always found that it's always the same number, no matter how you split it or what you do. And
we also found that since they're always the same number, and this is just 5 plus 4 plus 3 plus 2 plus 1, it's always going to be a triangular number too.
yeah.
And it's going to be the n minus 1. No, n minus 1 triangular number.
Yeah, so like since like we conjectured that it was always going to be the same, and we know we can always split it like so that it's triangular numbers, right? So then we know it's just 1 plus 2 plus 3 all the way to plus n minus 1, right? Because it's 1 plus 2 plus 3 plus 4.
And for this example of 7, we have 6 plus 5 plus 4 plus 3 plus 2 plus 1. And we know that for the formula for the n minus 1 triangular number, it's just n times n minus 1 over 2.
Yeah. So, okay. Okay, so now we thought that for any n, the score would be n times n minus 1 over 2. So that was like our conjecture. So.
Move it down.
So after like trying out a whole bunch of stuff and going nowhere.
Oh wait. No, we should show them the table.
Oh yeah.
Oh.
So we made this beautiful table with like what happened at every single step, and then it kind of came out to nothing, but it was pretty.
In this table, we tried out splitting it so that you split it as each pile as evenly as possible.
Yeah. So for example.
So like either you're splitting it, if
well,
it's even, you're splitting it into 2, or if it's odd, you're splitting it with 1.
Yeah.
So for example, when we have 10 chips, you split it into 5 and 5, so that's 25. And then you split each of those 5s into 2 and 3, so then you get a total of 12.
Well, and so we also had like levels. So we would keep track of like every single split, and we would call it a different level. So, and it's always, and since we're splitting it as evenly as possible, there would always be like close to the same number of levels, but sometimes there would be like an extra level. And we noticed all these cool patterns in the table, like, so.
These are all triangular numbers, because if you have an odd number, then when you divide that into 2 piles that are going to be like, that are going to be 1 apart, that's n times n minus 1 right here. And then we also noticed that basically going down the table, it was almost always dividing by 2, but not quite always.
Yeah.
So these yellow numbers are all triangular numbers.
Yeah, and we also noticed, so like here we noticed that it goes plus, so for example in this row it goes, plus 1, 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 all the way up to 16, and then it goes plus 2, plus 2, plus 2. And then in this row it goes plus 1, plus 1, plus 1, all the way up to 8, and then it starts going plus 2 after 8. And then for this row it goes plus 1 all the way up to 4, then it goes plus 2 after 4, and then at
12.
And then and 4 more, then it goes plus 3, and then 4 more goes plus 4, and
So that's what these
yeah,
numbers
and we had like all these cool patterns, and it just kind of
Yeah.
Yeah.
Oh, and then these numbers are numbers that we would put like the two methods that we had of doing it, like as we showed at the beginning.
Okay.
The like this method, and this method, we would put them side by side and calculate the difference at every level. And something totally weird that we noticed, but we never like really explored or anything, is that it always seemed to end in a minus 4.
Yeah, it was
Which is kind of weird, but we never really went into that part.
Well, so our first method of trying to prove it was so how we first tried to prove it was, so we say we have n equals 7. So first we would say at each level try to split it so like the product is the least possible. So that's when it's 1 and 6, and the greatest possible product is when it's
3 and 4.
when it's as close together as possible. And so we were gonna try to prove that if you split it every time so that it's the lowest possible, that it's gonna be like the lower bound, and if every time you split it, if it's the highest possible, then that's gonna be like the upper bound. And then we were gonna try to prove that the upper bound and the lower bound would be equal, but then we found an easier way.
Yeah, much easier.
Okay, so now you guys can do the
Okay.
proof by section.
So,
we
as we said before, the form, our like conjecture formula would be the n minus 1 triangular numbers, which is here. So
for induction, you have a base case. So this was our base case. If n equals 1, well obviously you can't split it, so it's 0. And if n equals 2, then there's only one way to split it, and the score is 1. And if n equals 3, then there's also only one way to split it, and the score equals 3. So those are our base cases.
Well, yeah, like
And
you
they
only
follow-
really need one.
And they
base
follow
Oh,
the
yeah,
formula.
Yeah, they follow the formula.
we decided not to use 1 as a base case because that was just kind of odd that you couldn't
Degenerate.
split it all.
Yeah, but like.
So we decided to just call the number of elements is n. Then you can split n into k and n minus k. And from here you can almost like erase this part and go along like this as if this didn't exist, and it's thinking with this number.
What I think what Michael's trying to say is
It's
that
basically, and this equals basically just what the sum of when you split k, what that equals, plus the sum of when you split n minus k, plus k times n minus k.
yeah.
And because this is induction, like we know that for k and n minus k, we can follow the formula.
Yeah.
Yeah.
So by like induction, we're gonna
And
say that everything up to n follows our formula, and then we are trying to prove if everything up to n follows our formula, then n will follow our formula.
And then you just mash that all out, and it comes out to n times n minus 1.
Yeah. So if you bash it out and you get like the score of k and plus the score of n minus k plus k times n minus k, if you simplify all of that, it simplifies down to. Yeah, it simplifies down to that, which means that if everything up to n works, then n also follows the formula.
And because 1 works, then everything.
Yeah, yeah. So then we've proved that they're always going to be the same.
Yeah.
So at every step, the score is n times n minus 1 over 2.
And then we wanted like a prettier proof because
Yeah.
that one was kind of like bashy and algebraically.
Yeah.
So this isn't totally a proof yet,
Well,
but,
it's kind of like a visualization / explanation.
Yeah.
but it's pretty proofy.
It's yeah. So we said to start off. Wait, do you just want to go to the page and say how we split it? Yeah. There. Okay, so
So we start off with a line segment of length n, and imagine for here that that's 7, right?
yeah, that's
Okay.
7.
So how we can split 7 into any way, let's say split into 3 and 4, right?
Yeah.
So then what we would do is we have a rule that you always fold down the shorter side. So you would fold down the 3 and create a box that was 3 by 4.
And by creating a box, you're calculating the area, which is equivalent to multiplying the two scores together, right? And so at every step, if you calculate the area, your final score is simply going to be the area of the figure we get, right?
So now we continue to split this.
So we split the 4 into 2 and 2. and then we split the 2 into 1 and 1. And so, and now we have to split, okay, so now, okay, so we split this 2 into 1 and 1. We also have to split this 2 into 1 and 1 because, and we have to split this 3 into 2 and 1, and then while I finish it. And then, yeah, so that's kind of our visual geometric representation of pile splitting. And so split 7 into like 5 and 2, do another case. And so we realized that this rectangle is 7 by 6, right? And we also realized that this is a staircase pattern, and if you take the staircase, rotate it, you can fit this staircase into here, right? So then we realized that this area, which is our final score, is n times n minus 1 over 2, right? So Lolly's now splitting it into a different method.
We figured out why this length would be n minus 1. Because whenever you split it, you're almost like moving a part of the segment so that it becomes vertical. However, like at the very end, this piece right here can never move.
Oh, yeah. Yeah, so like for example here, this segment goes to this, right? And then after that, you have this segment left. So then this segment right here goes to this. And then you have this segment going here. But you can't have this segment folding up because otherwise you're going to get like a 0 by 0. So that's why it's always n minus 1.
And that...
Yeah, well, we actually have a picture of like mapping it out.
Yeah.
So we noticed that it's always a staircase pattern, like it's always gonna look the same, right?
Because you can't have an edge that's more than 1 by 1 because then you have to split it more because you can't have a pile.
Yeah, exactly. Like you can't have an edge that is
like 2.
Yeah, that's like 2. So we just wanted to prove that it's always going to be like the staircase, because if we prove, so we know that it's going to be contained in an n by n minus 1 box, right? And if we prove that it's always going to be a staircase going 1, 1, 1, 1, 1, 1, then we know that it's always going to be n times n minus 1 over 2. And we know that it's always going to be a staircase that's going 1, 1, 1, 1, because we have to keep on splitting it until it is 1 by 1 by 1. Otherwise, if it's not 1 by 1 by 1, you have to keep on splitting it until you get to that point.
So,
oh wait, which rectangle? Oh, well, why does it have to be rectangle? And it obviously has to be rectangle because that's how we defined it to be. And so yeah, that just is like a visual representation of pile splitting.
Nicer than the fashion.
yeah.
And so yeah, that's kind of like our proof. Like it's not altogether clear why it's always a staircase. Oh, also wait, hold on. So, oh, and so this is like us. Oh wait, no, Lolly already did that. So, okay, so sometimes Lolly. So what we would also discover that. So say you have 7. Okay. So and you split it into 3 and 4. So say you draw this 4 up here like this. So if you're going to split it into 3 and 4, we define splitting as like, if you're splitting into 3 and 4, then we define splitting as you always like fold. So we said we were folding this to here, we're folding this segment to here, and we always define, you always fold the shorter segment up, because otherwise there will be some cases where you won't get the staircase and it gets really messed up because like it always needs,
It's just like really weird.
Yeah, it becomes really weird because like you'll get some cases where you're gonna get like boxes
like 2 1 by 1 boxes next to each other.
Yeah.
So it doesn't, like, make sense.
Yeah, and then it doesn't make sense anymore. So we
It's
just
very
define
hard.
folding to be you always fold the shorter side up because otherwise it doesn't make sense. And yeah, so that's
Our
proof.
presentation.
Yeah.
Wait, jump on.